Welcome to Breadboarding. In the previous video we managed to get our CGA graphics card built on solderless breadboards working to a large degree, and this is one of the test patterns that we finished the video on. However, there were a number of the tests that we did during that last video which had some interference on screen, so I'll just flick through a couple of captures of those screens. So this is a text screen which should be blank and just a flashing cursor at the top left here. You can see there's quite a lot of these symbols here. Then this is some of the 4-color tests, and you can see these various random pixels and things appearing. And similar for the palette test, we've got all these random pixels. Now some screens were better than others, so the high-res graphics here had very few. But this particular linearity test here, you can see it's supposed to be just a dotted grid, and there's an awful lot of interference there. And this one here was horizontal and vertical sync bars which were moving backwards and forwards across the screen, and this really left a big mess. So some of the screens were pretty okay, but some of them obviously had this fairly significant timing problem. And then the basic bouncing ball also produced quite a lot of interference. So this is video 58 in the Breadboard 8088 PC series, and this is the 13th part of the CGA video controller. Now in the project we've already developed a basic Nanocomp 8088 with an LED display and keypad. We then extended this to make a basic floppy disk PC with monochrome display adapter video controller and a floppy disk controller booting MS-DOS 330. And in this stage we're working towards running an early version of Windows 1.0, 2.0, and to do that we need to get this CGA video controller working. Now what I've done is I've captured this screen and I've done some analysis on it, and I've been looking at this particular character down the bottom left hand side here. So this smiley face, if we actually look up here, is actually a 02 is the character code. This is appearing on row 23, although this is 1 indexed rather than 0 indexed, so it's really 22 and it's about 10 characters in. Now if you work out what the address of that is, you can work out, because it's basically 22 times 160 plus I think 18. If you convert that to hexadecimal it comes out at DD2. Now when I go into the memory and the keypad that I've got here for the monitor, I can go into that memory address and that is in fact 02. So it's definitely the RAM which has actually got this. It's not actually a real-time thing just caused by the data going from the RAM to the video control hardware. Is definitely a problem actually with the RAM. I've set up the logic analyzer on the various address lines and on the data lines and various other signals, and we'll just take a look at that and see if we can see where this come from. So here's the logic analyzer output for the period where this particular screen was being updated, and what I did initially was I filtered on the address DD2 and I looked at where the value for DD2 changed. It was originally I think a space, so that's 20 hexadecimal is a space, and if we go into this one here you can see here that DD2, the address, has changed to 02 there. So then I work my way back, then this one here again DD2 is also 02, and then went back to here again, this is still 02, and in fact when we went back to this one you can see that DD2 is in fact 20. So basically between this one here and this one here the value changed. Now there are only 3 writes going on here. When we drill down into this one you can see that this one has now changed to 02. When we first look at it, it doesn't seem to be any obvious time here. So if you look here, the 2 writes here are 05D2 with the 75 and 75. So if we go back to our screenshot, so in fact 75 is this U, lowercase u, and is this color combination. So basically it's outputting this particular character here, the U here, in that the character code is 75 and the attribute will be 75. So at that point in time this characters are appearing down here. Now down the bottom here what we've got is our CGA RAM chip enable, and we've also got the video RAM write signal as well. So unless there's something seriously wrong with the RAM, then it's only during one of these write periods where this is low where the RAM can be updated. Now when you first look at it, it doesn't really look like anything particularly interesting going on. We've got 3D2, 3D2, 0F, then 7.5. So 0F is generally the white colour that we have for the number labels on here. But when we drill down a little bit further, you can see that there's a bit of a blip in the addresses. Now, in fact, the blip is so short that the analyzer here doesn't actually decode it. So 05D2, 05D2, but in fact, you can see here there's an A11 here. Goes high momentarily, whether that be interference or whatever reason, whether it's just a difference in speed in changing. And if we work out what 3D2 plus that particular one is going to be, that's actually going to make it up to D. So in fact that blip there has caused it to go to D2, and we can see here as well that the data just for this period of time between going from 0F to 7.5 over here has briefly been 0.2, and so it looks like this has actually got written. Now if we see how close this is to the beginning of the write signal, this period here to this period here is I1 to I2, and that's 70 nanoseconds, and so this period here is probably about half that, 30 or 40 nanoseconds. So what the problem here really is that there's a period of time from that really it takes for the data and the address lines to settle. So if we probably cut this write period in half, so rather than it being at the moment, if you look at the top right hand side here up there, then that period is 375 nanoseconds. So the RAM we're using is very fast. It's 10 to 15 nanosecond access time, so that's probably one of the reasons why we're getting this problem, is because it's so fast it will actually update it in that brief period of time. So I think what we'll need to do is just to look at how can I shorten this particular period. Now one thing that I have done previously is use the dot clock, and I can either delay this period by one dot clock by putting it through a flip-flop, or we could use one of the QA or QB signals, which is multiples of the dot clock, or we could actually AND the value here or all the value here with part of a clock signal to shorten it, so it'll actually become a bit shorter. It's probably better to delay it, because otherwise what will happen is we could have some situations where the clocks come in and out of phase. So what I'm going to do is go off and actually look at how to address this. So we basically need to make this bit here move a little bit further over to here, so that all this stuff has actually stabilized by the time we get to it. So what I've done is quite a bit of analysis on the various timing signals here, and basically trying to get the write pulse here to start quite a bit later on in the cycle here, and actually shorten it a little so it finishes before the end of the memory write pulse as well. So in order to understand that, then what I've got here is just a chart over a number of clock cycles. So in the end, I found that using the CPU clock, so the 8088 clock, which is about 5.3 megahertz, I think it is, and that's in step with the memory write signal as well, whereas the video signals will go in and out of step with the CPU signal. So that made things simpler. So in green, the conditions that we previously had. So we have our CGA RAM chip enable, the memory write, and what we need to do is to take the memory write and CGA RAM, delay it by a clock cycle, so it shoves it over here, and then in fact by including it with the memory write and the clock signal, we can actually shorten it and make it a smaller pulse, and this seems to actually resolve the interference issues. So I've burnt those into the PLD. I also had to update the PLD to be a slightly larger one. So originally this was an ATF16-8, and because I needed this extra delay signal here, then I had to increase this to the larger ATF22V10. So this has 10 outputs rather than the other one only had 8 outputs. So I've now put the CPU clock coming in here, and if we have a look where it comes from, And basically this is the clock that's fed into the 8088 and comes out of the clock circuit up here. And the advantage of that is it means that it's always going to be in synchronization with the memory read, memory write signals and things. So here's the original PLD configuration file being compared with the revised one, and the main difference really is that we're now using the larger PLD. So this is the 2210 as opposed to the 16.8. So this means it has 10 outputs rather than 8 outputs. And as we go through the changes here, we've added the clock to change the video RAM timing. And you can see now we've got 24 pins here rather than 20 pins. And most of the changes that you see down the bottom below here are just the pin numbers and things changing. The output enable here has now been relabeled. This is the 646 output enable. This was not connected. Now I have wired up the output enable here just to be clear. Then you can see we've added the clock and the output enable down the bottom there, and just the pin numbers really have changed there. You can see that we've added the 646 output enable just to make it clear that that's for the other buffer chip. We've added the video RAM write enable delay, so this allows us to get 1 clock cycle delay to the signals that we're using for doing the write enable. Can see now that rather than just the simple rule that the write enable was the memory write ANDed with the CGA RAM, we're now putting memory write CGA RAM into the D side of the flip-flop, and then we're combining the output of the delay with memory write and clock, and that's giving us a shorter delayed write enable, which seems to resolve the problems. And then that's just the renaming of the output enable to be 646 output enable. So that's all been compiled and programmed into the PLD. So that was the only change that needed to be done here, apart from shuffling things around so we could fit this chip in there. What I'm going to do now is I've started up the breadboard PC. Just going to send our test program down again, share the video and run it. So we have the blank screen with the cursor on the top. Then we have our text of attributes, blinking, then our 40 by 25 mode, various 4-color graphics modes with various color palettes and intensities. Then that's the high-res mode with an alternating pixel, and then that's finished. So now if we actually boot DOS as well, we'll first go to Tools and do the CT tests. So that's the 40 by 25, the 80 by 25, the 4-color tests for the various palettes, and the high-res graphics mode. And the direct write ones work there as well. So now we'll run up CGA Comp. This is the most demanding utility. We're just going to go into the main screens that I showed earlier, which had all the interference. So the color palette tests all seem to be working now. Horizontal retrace is one of the more demanding ones. That's with start address reprogramming. So linearity was one which had probably some of the worst examples previously. That's clean, and so's the dotted one. Motion test plate was probably the most demanding one and was a real mess previously. And although we have the snow, there are no stray pixels left behind at all now, so these vertical and horizontal bars are not actually creating any leftover pixels. I was pleased with those updates. That seems to have cleaned things up quite a bit. There was one other thing that we also had in the previous video. So one of the other problems we had is that the cursor wasn't coming out in quite the right place in DOS and some other times in some of the other tests. And the reason is that the original CGA card had lines 0 down to 7, but because we're running on VGA, we're actually doubling those up, so it's really, there's 16 lines for each character. We're just double scanning each row. But that means that when the cursor is set to be line 7, it's actually halfway down the character. So what I've done is updated the BIOS code so that it actually doubles the value when using the BIOS. If certain programs directly write to the cursor registers without going through the BIOS, then in fact this won't work. So in fact, when we have a look at DOS now, you'll see that in fact the cursor is now in fact an underscore there, and if we reboot, the cursor is also coming out as the underscore there. Should say the only issue with the CGA comp test program, it must be updating the cursor directly into the registers. Because when we try the test for the cursor in CGA comp, then in fact it's still not working quite properly. So you can see the regular cursor is still halfway, upside down cursor is at the top correctly, but the full block cursor is not the full block. And that'll be because probably the test program is directly writing to the registers for the CRTC without going through the BIOS. We just have a look at what change was necessary to do that. So in the set mode cursor shape here, what I've done is put in some stuff specific to the breadboard PC. We don't do anything if we're in the monochrome display adapter, but otherwise we actually multiply the start row by 2 and the finish row by 2, so we rotate it left, and then we update the cursor start in the CRTC. So this will mean that anything using the BIOS to update the cursor shape will work, but if there's a test program or something which writes directly to the registers here, then they will have 0 to 7 rather than 0 to 15, which is what really this needs. So the main fixes I want to do in this video. What I'm going to be doing in the next video is, this is a screenshot from the CGA Snow test. So this is deliberately manufactured by the CGA comp test. It basically tries to update the video RAM as fast as it can to generate as much interference as possible. You'll have seen in some of the other tests, then normal operation, you get some interference, but not as bad as this. There are a number of ways to address this, but I'm going to be looking at the hardware way that basically means there should be no slowdown in the software. There are a number of ways how you can address this. One of it is polling the various status flags and only updating the screen whilst the video is in the vertical blanking period, or some programs also blank the video signal whilst the RAM is being updated. This does result in video flicker. So if you don't want to miss out on future videos, then please hit subscribe And if you found the content interesting, please hit like. There will be a playlist in the description below where you can see all the videos in the series. Thanks for watching.